My name is Kazuma Nagashima from Shizuoka University. Today, I will talk about computational analysis of an actual-based curiosity model. Here is a plan for today. Let me start with some background. Why do people keep exploring the unknown, even without any external reward? Curiosity drives people to engage with things. It helps people learn in unfamiliar environments. We think understanding curiosity is a key challenge for cognitive science. To examine this internal process, we think cognitive modeling is needed. Based on Marr's framework, a good cognitive model should explain both why and how. First, it should explain the rationale, what is being computed, and why it is appropriate. Second, it should specify the mechanism, how behavior is generated. Two approaches have been proposed for models of curiosity. Computational approaches ask why and what curiosity computes. Cognitive architecture approaches ask how curiosity is realized. Each approach answers a different question, so there is a gap between them. We think that two levels must be bridged. Next, related works. First, Marr's three-level framework gives us a way to describe this question. Marr proposed that cognitive system can be analyzed at three different levels. As shown on the right, computation level. Why is it appropriate and what is being computed? Algorithmic level. How is it computed? Implementation level. How is it physically realized? Marr argues that understanding cognition requires connecting these levels. Based on Marr's framework, here is a computation level account of curiosity. The free energy principle is a Bayesian model that homogenizes why and what cognition computes. This principle proposes that brain minimizes free energy, balancing complexity and accuracy. Complexity reflects the gap between prior and posterior belief, and accuracy reflects how well prediction match sensory input. For example, when predictions don't match sensory input, the accuracy term decreases and free energy increases. Thus, higher free energy indicates larger prediction error. From this perspective, curiosity arises to reduce this free energy through exploration. This principle has been applied at the implementation level through deep reinforcement learning with intrinsic motivation. Curiosity is used as an intrinsic reward, driving the agent to explore. However, because these models are end-to-end, the connection between the computational and algorithmic level is lacking. To address this gap, our goal is to connect an algorithmic level with computational level. Our method is to analyze relationship among simulation results using a Bayesian network. We map the model's behavior to a computational dependency structure. Before presenting our method, let me introduce a cognitive architecture model at the algorithmic level. For the algorithmic level model, we use ACT-R. ACT-R is one of the most widely used cognitive architecture. As shown on the right, it consists of multiple modules grounded in human cognition. In our model, Curiosity is implemented by combining these modules. The core idea comes from Schmidt-Huber work. Curiosity is defined as discovering compressible data. In Act R, retrieved knowledge can trigger production compilation related to compression of rule through pattern matching. We assign a positive reward to this event. This is our assumption of how curiosity arises in Act R. Based on this idea, we created a framework. This flowchart shows how the agent explores an environment in each round. The key point is that the agent tries to retrieve information during tasks. If pattern matching occurs, rules are compressed and the continued rule receives a positive reward. If not, compiled rules are used without compression, and the continued rule receives a negative reward. This cycle repeats across multiple rounds until the agent stops. We describe the simulation setup. We manipulate three factors: curiosity strength, task difficulty, and level of thinking. As shown in the figure, there is an optimal level of curiosity for performance. This optimum shifts with task difficulty and level of thinking. Next, I will explain difficulty and level of thinking in detail. To manipulate difficulty, we use a maze exploration task with three sizes. The agent starts at S and reaches the goal G using four actions: north, south, east, and west. Each size has 10 different maps. Each round has a time limit of 180 seconds, and the total task runs for 3,600 seconds. The model repeatedly explores the maze across multiple rounds within this time limit. To manipulate level of thinking, we compare three models that differ in cognitive processing. The random model selects paths at random. The DFS model uses depth-first search. The DFS+IBL model combines the DFS model with instance-based learning. It retrieves past successful experience, which trigger pattern matching. Third, cognitive processing, which is related to level of thinking, increases from left to right. We evaluate each model using 5 measures. Uptime ratio reflects engagement, and rounds measure persistence. Entropy track exploration breadth, and goal rate indicate performance. Finally, prediction reflects the knowledge built up during exploration. We run simulation to observe how these measures behave across models and conditions. Each panel shows strengths of curiosity on x-axis, one measure on the y-axis, and each column shows one model, and each line represents a different maze size, which is environmental complexity. This slide has two measures about uptime ratio and rounds. I briefly summarize the key result. Uptime ratio increases with both complexity and curiosity strength. This indicates that complex environments stimulate curiosity. This slide has three measures about entropy, goal rate, and productions. The key point is stronger curiosity improves learning in the DFS+IBL model, while it had negative effect in the random model. only DFS plus IBL has memory of past successes, so curiosity improved learning. This indicates that learning is most effective for the highest cognitive level. Next, I'll use the Bayesian network to analyze the simulation at the computational level. Actual behavior comes from many interacting rules and manipulated variables, so single measure cannot capture the overall structure. By recognizing these interactions as dependency, we can redescribe model behavior at the computational level. We apply a Bayesian network over variable and measures. Variable as the curiosity strengths for each models and map sizes used in the simulation. Measure are also around entropy, goal rate, and productions. Uptime ratio is exclusive because it almost overlaps with rounds in the causal chain. The Bayesian network will describe these dependencies at the computational level. Each arrow indicates that one variable has a positive effect on the next. This is hypothesized our causal network. Each arrow is a conditional dependency, and each node is a linear function of its parent. J influence flow from curiosity and map size through goal rate. Based on this network, we expect the following effect. First, higher curiosity led to more production because stronger rewards increase pattern matching. Larger maps also produce more productions because they contain more patterns. Next, more production led to more rounds because compile rules enable more efficient exploration. Next, more rounds led to higher entropy. The agent covers more of the environment. Finally, broader exploration increases the chance of reaching the goal. This slide shows the regression coefficient. Each value is a standardized coefficient and larger means a stronger dependency. The difference is clearest at the end, where entropy has a stronger effect on goal rate in DFS plus and DFS. To evaluate the fit on the network, we examine the BIC. Less negative value indicate a better fit. The BIC confirm this, and DF plus IBL and DFS fit the network well, while random does not. By describing actual behavior as a Bayesian network, we can redescribe it in computationally interpretable terms. Our method bridges the algorithmic level and computational level. In conclusion, we show that measures from interdependent structure, DFS plus IBL and DFS show a coherent dependency structure, while random does not. Our method makes algorithmic level behavior computationally interpretable. For future work, we plan to collect human data and compare their Bayesian network. That's it.